Okay, things for us to know. Homework due on Wednesday. Exam next Friday. You will have a study guide by end of day tomorrow for some list of topics for that. At some point next week, we will just have a review session. It's a very small class. I just kind of want to get people's opinion on when that study session would be most useful. To give you an idea of the variables that might be at play for that, you're going to be turning in an assignment on Wednesday. The material on that assignment will be on the exam. Hunter, I've told him that Thursday morning, it's his job to grade everybody's assignments, especially in a small class. So that should be turned around, hopefully by about noon on Thursday. But we don't meet between then and the Friday morning that we have the exam. So we could do the review on Thursday to be the day after you submit the assignment so that we can discuss any aspects of the assignment after submission that you felt like you could use some additional clarification on, additional practice problems with, something of the sort. But I also like there to be a little bit of back and forth so that I can prepare that in advance. And go away teams. So are there any thoughts or opinions on when that would be most useful to you?
I like the Thursday idea. I think
Thursday idea. We could do it before that, and then it might be useful to you as you're doing the assignment to get some extra practice problems so that you can iterate on that. That'd be the argument for earlier. Again, I'm not saying one's right or one's wrong, but I've had that argument in the past. If it's better to have it earlier so that you can iterate on that experience that you get from that review session, apply it to the assignment before you turn it in, but then it's farther or further away from the exam. It's not a distance, it's a measure of time. So
I'm fine with Wednesday or Thursday.
Wednesday or Thursday? I guess I'll query more people when we have more people, but that's kind of that's where we are. The important dates that are coming up, just assignment Wednesday, exam Friday, study guide by this Friday, so that you can at least start thinking about the topics, but they're mostly the topics that we've covered and are on the current homework. So last time we learned about non-determinism, we learned about non-deterministic finite automata, and we constructed a couple of NFAs for these exercises. I kind of want to go back to the definition of NFAs just for a second, because we're going to be today doing DFA to NFA conversions. And so there were three very important distinctions between DFAs and NFAs. What were they? Differences between DFAs and NFAs.
NFAs have a lambda transition where there's nothing.
Yes, we allow lambda transitions, which I like to think of as just teleportation between two states. You can move from one state to another without consuming an input character from the input string. So that was that one. What were the other two?
So I can have multiple
Yeah.
transitions based on an input.
Yeah, so if you're in a state and you want to be able to read a particular character, you can now have multiple possible transitions out of that state. So multiple possible transitions that consume the same input character. So we can go from Q0 to Q1 on an A, or we can go from Q0 to Q2 on an A. The last one was the kind of least important, but you don't need to specify every possible transition. This does not need to be a total function, meaning that we don't need to think about or construct trap states. So here was just kind of a drawing that had all three of those in as simple a way as possible, even though this state machine doesn't really make a ton of sense. Overall, the concept of non-determinism is basically, what if we could take a branching statement and explore all of those branches all at the same time? The other way to think about it is it's a verification algorithm rather than a determination algorithm. So rather than cracking my password, I tell you what my password is and you verify yes or no that it is my password. So that's what we covered last time. And now we want to go into the actual process of, the reason behind this was sometimes it's easier to construct an NFA than it is to construct a DFA, just because we have all of these extra options. And we also learned that the class of languages that an NFA can accept is no different from the class of languages that a DFA can accept. Basically, if we can draw one or the other of these, we can draw the other one. There will be at least one equivalent DFA for a given NFA. There will be at least one NFA for a given DFA. Usually infinite. One way to think of a DFA is that it's just a restricted NFA. There are some aspects of the NFA that we don't allow. So you can think of a DFA has a bunch of possible equivalent NFAs. You could just argue, for instance, that I'm just going to add an infinite number of states and add lambda transitions from all of the actual states of the DFA to all of those infinite number of states. Now take any subset of those infinite number of states and you have an infinite number of NFAs for a particular DFA. And that's just considering the first rule. So any DFA is going to have an infinite number of equivalent NFAs, and they're all going to be, well, some of them are going to be useless, and some of them might reduce the number of states of the DFA and make them easier to put into memory with these associated rules with them. But the question that I might have for you is the converse true as well? Anyone remember the definition of a converse from discrete? So the statement is if A, then B. The converse is if B, then A. The inverse negates both. If not A, then not B. The converse swaps them. If B, then A. And the contrapositive swaps and inverts. So it'd be if not B, then not A. So does an NFA, a given NFA, have many possible DFAs?
Go ahead and say no.
Yeah, I want to say no as well.
Yeah, it actually is basically true. There's at least one DFA, a process of which we can reduce this down into a particular DFA. And so the question now is just, what is that algorithm? How could we take an NFA and the rules of an NFA and convert that into an equivalent DFA? So just take 30 seconds and start to process that. If you were tasked with, and this had never been done before, we want to take as input an NFA, produce a DFA. Where would you start? What would you do? What do you think is required as part of that translation process?
Potentially involve adding more states to the NFA.
Yes,
Okay.
that's a great intuition. What are those states representing? Would be the next question that I would ask back at you.
Potentially some of the trap states, maybe, and
Okay, yes.
I'm not sure.
Yeah, that's a tough question. I like posing tough questions because we're going to go through kind of a proof type of how we can do this in general. So with any proof that I want to give people in class, I could just write out, here are the steps for how to do it and move on. And that's not useful to very many people. So I like you to start with the kind of thinking about the intuition of it yourself. I'm going to go at it in an intuitive, non-technical way to give you the, here's why it makes sense that we do it this way. And then we're going to go through the technical process. So hopefully that helps it stick a little bit better. So let's start with the intuition. All right, so after a DFA reads a string, let's say we hold the string constant. We're in binary 10010. For any given DFA, how many possible states can the DFA finish in after it's finished parsing that string.
Is that an accepting and a non-accepting state, or?
Not necessarily,
Okay.
but like, let's say we have a DFA with 5 states, Q0 through Q4. Doesn't matter what those states are, doesn't matter what the transitions are between those states. But if it's a DFA and we finish reading this string, what possible subset of these 5 states could we be in? The actual construction of the DFA doesn't matter, the string doesn't matter. There's a correct answer. Because it's a total function. When you read the first input character, there's only one place you can be, because there's only one transition out of that initial state that reads that character. From that state where you are right there, when you read the next character, there's only one state you can be in, because that transition is defined. By the time you finish, there's only one state you can be in. There are no options in a DFA. There's no optionality. We added that optionality with the NFA. There were lambda transitions where we could take it or not take it. There was the possibility that we had 2 different outputs from the same, 2 different transitions from the same state that read the same character. So we could go to this state or that state. With a DFA, there's one and only one. There aren't 0 and there aren't 2 or more. There's always exactly 1. So it's predefined exactly what's going to happen as you parse this string character by character, which means that by the time you finish it, you're in a particular state. It's defined by the definition of a DFA. I'll ask you the same question about an NFA. How many possible states could it be in? Yeah, any of them. You could define an NFA such that basically we don't know, but it could be up to all of them, but some subset of them. But now it depends on the string and it depends on the NFA. So some subset of the available states. So the basic intuition of how we're going to do this conversion is that we need to add states to the NFA that represent every possible subset of states of the DFA. Or at least that defines the largest the DFA could be. Because they represent different subsets of states. When you could be in multiple states in the NFA, you make a state in the DFA that represents that you could be in that particular subset of states. I think that'll become clearer as we have an example of this process, but we're going to add, let's say we have an NFA with Q0, Q1, and Q2. So I'm actually going to draw this. The DFA, NFA, I want to start with the NFA. We'll do this reverse. Has states Q0, Q1, and Q2. Finality does not matter here for the moment. The DFA, when we go to convert this NFA into a DFA, is going to have these same states. I'm actually going to leave a little bit of space up top. Q0, Q1, and Q2. But it's also going to have a null state that says that it's not possible to be in any of the states of the NFA. There's also going to be a state called Q0, Q1, another state called Q0, Q2, another state called Q1, Q2, and another state called Q0, Q1, Q2. So we're going to blow up this NFA into a really large structure, potentially. Sometimes not all of these are required, but this becomes the largest that the DFA could be. What's the relationship between this? What are the maximum number of states of the DFA given the size of the NFA? What's an expression that could map that? Given this, we get that. Yeah, 2 to the number of states in the NFA. We see 0, we have 1, 2, 3, 4, 5, 6, 7, 8. And again, just like we saw on the first day, if we break this down into the size and the number of states, there's 1 of size 0, 3 of size 1, 3 of size 2, and 1 of size 3. That's our friend Pascal's triangle again, as we're talking about combinations again. So everything from discrete just kind of comes together and helps you to be able to understand different aspects of, since this is just a subset, the number of subsets of this becomes the superset of that, which we talked about on the first day. Now the question is, how are we actually gonna go do it? So we need to add transitions between these states based on what you can reach by reading each possible input character. That kind of is a bunch of gibberish. Let's find out what that means with an example. So does doing this result in a DFA? You need to have a total function if you do this. The answer is yes, it does. So how many states from the associated DFA? We figured this out. 2 to the number of states in the NFA. Let's go through an example. Here is an NFA. So if we want to go through this transition process, we're going to start with the state that is the starting point for this Q0. And we're going to do exactly the same thing as we draw the DFA. So we're going to draw a state that we're going to label as Q0. Note that this doesn't necessarily have to be the case. There is one thing that this NFA could do that could change the state that we start at in the DFA. Any intuition as to what that might be?
Except for the B in the beginning.
Close, but not quite. So it's a good idea. The answer is if there's a lambda transition out of Q0, because we could teleport to that without consuming any input characters. So the question is, this is the subset of states that you could be at in your NFA without consuming any input characters. So since there's no lambda transition out of Q0, we're going to start this at Q0. Now we need to figure out what are the subsets of states that we could be in with every possible character that we can consume from Q0. So from Q0 on an A, what are the set of possible states that we could be in? Just Q1, we're going to make a transition to a state that we're going to call Q1 on an A. That's the only state we can get to. Since Q1 is final here, this Q1 is also final. The general rule for this is going to be if you have multiple state names in your particular state, if at least one of them is final, then that state is final. So the state Q1, Q2, if we end up needing to make it, will also be final. Q0, Q1, Q2 would also be final because at least one of those states in the NFA is final. All right, is this a total function yet? And for this to be a DFA, we need to have defined transitions out of each state for every possible character in the alphabet. As soon as we have that, we have a total function we can stop. But no, Q0 needs to be defined on a B. What are all of the states that we can get to from Q0 reading a B? None of them? We can't get anywhere. So we're going to define a new state. Remember that we had the null state before. We're going to define a new state that we're going to call the null state. We're going to transition from Q0 to the null state on a B. The null state by definition is a trap state. So we're going to draw an arrow like this on an A or a B from that null state, because we can't get from no state to a state. There's no lambda transition from nowhere into this NFA. It's kind of the intuition for how you would think of this. All right, Q1. Q1 on an A, what are all of the possible states that we can get to from Q1 on an A?
Itself.
Just itself. Is that true? We can go Q1 A.
No, there's a lambda.
There's a lambda. And in fact, we made a mistake when we did Q0 on an A. Because we can also get to Q2 without consuming this. So this should actually be Q1, Q2. My apologies. So now the real consideration here,
Is it still a final stage? Or?
it is still a final state, yes, because at least one of these states is final. That means there exists a path from Q0 on an A that ends in a final state. You could be in Q1 or you could be in Q2, but since there exists a path to a final state, the result is a final state. Great clarification. So when we see a state here with multiple names associated with it, you have to ask from either of these states when we consume an A. So now you're going to say, what can we do from here or here consuming an A? So where could we be in Q1 or Q2 if we consume an A?
Q1 or no?
Q1 or Q2. Yeah, so I guess you could land a transition here and then consume the A and be null. Luckily, null is never going to be a member of one of these other states. That's only if there's no other state that it could be in. So we're never going to concatenate null to any other symbol. That's a great clarification as well. So the answer is from either one of these places, we could be in either one of these places. That tells us that we loop from Q1, Q2 to Q1, Q2 on an A. Does that make sense? We go from either being here or here, consume an A, we could either be here or here. It's the same subset of states, so that tells us it's going to be a self-edge.
So why again, if we were going from Q2, why can we not go back to the null state if A doesn't have?
We could.
Oh, okay.
We could, but we never concatenate null to
I
anything else
see.
because it's just a trap state. It isn't necessary to create the total function of the DFA. We only care about transitions that are relevant. And since the DFA can't have an A down to the null as well, and there'd be multiple edges out, that just kind of becomes an instant failure. The NFA has potential for kind of an infinite number of, well, we could just fail. The question is, if we're on the path to success, what are the subsets of states that we could visit? I guess might be the way to think of it, but that is a great point, great clarification. Yeah, this is only a state existing by itself. We transition there if the subset of states is none. All right, Q1 or Q2 on a B. What are the possible subsets of states that we could be in? We must consume a B.
Q0.
Yeah, if we're in Q1, there's no possible way to consume a B unless we take this lambda transition and consume the B, in which case the final state that we're in is Q0. From Q2, the only transition with a B is Q0. So the subsets of states from Q1 or Q2 on a B is back to Q0. We have a total function. Yes, we do. So we don't need any of the other sets of subsets of states. This is it. By the time this process terminates, you have a DFA. Tim.
Seems like for the most part, all you really did was like close that gap with the lambda.
Yeah. There will be much more complicated examples that we will get to. I did this one as the initial one because it is the simplest one that terminates the fastest. To kind of talk about the why. It includes the null, so we can talk about that. It includes a state with multiple states, so that we can talk about that. But other than that, it isn't a long drawn out process that involves 2 to the 3 number of possible states. That's the largest that the resulting DFA could be. So some considerations, we've probably gone over most of these. The initial state of the NFA is Q0, so the initial state in the DFA will be Q0 plus anywhere we could get from a lambda transition. So this isn't quite complete here, plus anywhere else that we could get with a lambda transition. We've already done this. Transition from Q0 reading in A means the NFA could be in either Q1 or Q2. So we make a state Q1, Q2 in our DFA, transition from Q0 to Q1, Q2 on an A, which we've already done. It's a final state because at least one of the states in the subset was a final state. So it's possible to reach acceptance in the NFA. Remember that an NFA allows us to branch and explore both. If one branch leads to failure and one branch leads to success, there exists a possibility of reaching that success. So we pick the one that leads to success. Part of that just non-determinism. Transition from Q0 on a B, no associated state. We need to make a non-final trap state, which we do with the null. Determine the outgoing edges for Q1, Q2. We did that. Q1, Q2 on an A leads to Q1, Q2. This is one way that we can specify that transition. This is a state that involves multiple NFA states, comma, the A. This usually actually has a tuple around it to show that this is one structure. The structure is the state symbol resulting state. Fun. So this is everything that we just did. We never ended up in Q1 or Q2 by themselves. We only ever ended up with them together, which kind of makes sense if there's a lambda transition between them. If you can visit Q1, then you can also visit Q2. Note that that wouldn't be the case if we had an incoming edge that wasn't a lambda to Q2, because this is not a bidirectional lambda. We can't teleport between them, just from Q1 to Q2. So if there were an incoming edge to Q2 that weren't a lambda, we probably would have a Q2 somewhere in the DFA. So there are some states that are not necessarily in the associated DFA. You just continue to build the DFA until you have a total function. So all transitions are defined. So the resulting DFA looks like, hopefully, what I drew. That's pretty good. In fact, I didn't look at this ahead of time. The placement is kind of the same too. That's kind of scary. We ready for a practice problem? Do we feel like we understand the algorithm for constructing a DFA from an NFA at an intuitive level? Let's give you a chance to work on it. Feel free to pair up, get in small groups to work on this together if you would like to do so. And let me erase this so you can actually see it. Here is an NFA. This 0, 1 represents a multi-edge where you can get from Q0 to Q1 on a 0 or on a 1. Start by thinking about what is the starting state, sets of states out of that starting state, sets of states out of those states, until you reach termination, a total function. This one's a bit harder, isn't it? If yours terminated early, reconsider, reconsider your process. How do we get started? I at least want to get this process started in case you're at a particular point and are having trouble continuing. So where do we start with this? What is the DFA's starting state? Q0. Let's see if I can fit all of this on a screen. Can be kind of small. Great. From Q0, now we're just going to start iterating this process in a loop from every possible place from here. What are all the places we can get to based on every possible character in the input alphabet? So on a 0, where can we get?
Q0 or Q1.
Q0 or Q1. So we're going to, on a 0, make a new state Q0, Q1. How about on a 1? Q1, that is a distinct state from Q0, Q1. So on a 1, we're going to go to Q1. Great. Now we need to do this again for each of these states that we've made. So let's start with, I don't know, any preference between Q0, Q1, or Q1? Where should we start? Let's start with Q0, Q1. Why not? So from Q0 or Q1 on a 0, where could we get?
All three.
All three? I didn't forget to mention these are both final states because Q1 is a final state. So here on a 0, how do we want to do this? Okay, so let's do this here and we'll see how bad this makes my drawing. So another state, Q0, Q1, Q2, since at least one of those states is final, this state is final. How about Q0, Q1 on a 1? How do we get from, yeah, you're right. Q0 to Q1 on a 1, Q1 to Q2 on a 1. So we need Q1, Q2, another state that we don't have yet. Since Q1 is final, Q1, Q2 is also final. Great. We've made an even bigger problem. Even more nodes here, vertices without outgoing edges. Which one do we want to focus on? Now we have 3 options.
Q1, Q2.
Sure. Where can we get from Q0, Q1, Q2 on a 0? From any of those, we could reach any of them. So this is going to loop to itself on a 0. Does it make sense as to why that is? From Q0, we can reach Q0. From Q0, we can reach Q1, and from Q1, we can reach Q2. So from this or this or this, we could reach any of them. How about Q0, Q1, Q2 on a 1? Q1, Q2, we can't get to Q0. That can't be the destination on reading a 1 from anywhere. So the transition is going to be from Q0, Q1, Q2 on a 1. All right, how about Q1, Q2? Where can we get on a 0?
Q2.
Q2, another state we don't have yet. It's not final because Q2 is not final. So this transition on a 0. How about on a 1?
Q2.
Just Q2? You can add a multi-edge, especially in large complex diagrams like this. That is perfectly fine. You can also draw 2 edges, each of which have a different transitionatory character of the alphabet. Either notation is fine. Don't worry about it. Excellent. Q1 or Q2? Which one do we want to focus on next?
Q1.
Q1. From Q1 on a 0, where can we get? Same with a 1, right? We can only get here to there on either a 0 or a 1. So we're going to add a single edge here on a 0 or a 1. How about Q2? Where can we get on a 0? Nowhere. So we need to make a new null trap state that we transition to on a 0. How about on a 1? To itself. There we have a final DFA for this NFA. It got much more complicated.
I started doing this and then I was like, this is too complicated, I'll probably do it here.
The only state that wasn't in here was Q0, Q2, right? So we got 7 of the 8 possible states. So it can turn into something that's pretty complicated, especially if the NFA has significantly more states than 3. Remember, we're doubling the potential size of the DFA every time we add a single state into the NFA. That's kind of gross. Exponential complexity is a bad thing. But at least we have an algorithm that converts between one and the other. So if you're ever tasked with coming up with a DFA to solve a problem, one possible way to get to that DFA is to construct an NFA and then convert that NFA into a DFA. Questions on this solution? Anyone see any issues with it? Did I make a mistake? That will happen at least once, probably multiple times throughout the quarter, so feel free to call me on my bullshit. Yeah.
Do you need the self loop on the null state for the 0, 1?
Yes, we do actually.
Uh-huh.
It needs to be a total function. So good catch, very good catch. See, it didn't take very long to be called on my bullshit. It's like immediately. It's useful. I would rather give you the right information than the wrong information. Now do we buy it? Anyone need anything else from it before I erase it? Right. It's gone. It only exists on a recording on the internet. Hello, people watching the recording back. So here's kind of a midpoint. Here's the full solution. Here's the algorithm. If you were to read a textbook, this is what they give you. You're like, get it? And I don't think anyone really learns math or algorithmic processes this way. So I prefer the approach that we did. Thinking about it in the problem in the abstract, practice problems, going through kind of a step-by-step intuitive process, and then refining that step-by-step process into something that is technical. I would hope, though, that with the knowledge of these terminologies, that if we've gone up through the examples, that you could generate this. This is now not only readable, but it's something that you could have written with enough time and energy. So, create a graph. We have an initial vertex. Once again, this is slightly wrong. We want it to be an initial vertex of Q0 concatenated with or including any other state you can get to without consuming an input character. Even the book gets this slightly wrong. So repeat until no more edges are missing. Take any vertex with no outgoing edge and figure out all possible transitions of places that you can get to on a single character. For each possible character, reading that input from the input. And that will lead you to unioning all of those together to get the final subset of, if you can get to this state on an A, if you can get to this state on an A, you can get to this state on an A, take everything for which you have a yes, union those together into this set. You'll create a vertex for that, or if it already exists, you'll add an edge to it. That's basically it. I created this whole lecture off of this. So that's everything from this exact process, but we're going to go do something else pretty technical, because the reasoning behind converting an NFA to a DFA, we frequently want a DFA, but the DFA that we get from converting an NFA to a DFA is often large and complicated. Sometimes unnecessarily large and complicated. We could reduce the size of the DFA, either in terms of the number of vertices, the number of edges, both. And that allows us to have a better representation that will take less memory to represent, less time to fully iterate. That's actually not true. It'll take the same amount of time regardless, given a particular length of a string, but we know that there are many possible DFAs that accept a particular language. We want to know, is the DFA that I constructed, does it contain the minimum number of nodes or states that are necessary to represent the problem? So we want to optimize. So in what ways can we determine whether a DFA is better than another? We really can just look at the number of nodes, number of vertices, number of edges, basically. Fewer states, faster acceptance and rejection, and less storage space. As an example, the question I have for you is, here is a DFA. Can this DFA be reduced? If so, how? So we'll probably spend the last couple of minutes of class, since there's only a couple minutes left, staring at this, and I'll leave you hanging with no answer. And we'll come back to it. It's a reason to attend tomorrow, so that we can find the smallest possible DFA that we can get from this DFA. Heck, maybe it's itself.
Q5 unnecessary,
What makes you say so?
because you can't ever get Q5.
That's a great point, right? Yes, absolutely. This whole thing is completely unnecessary. We just can't get there in the first place.
Three is useless as well, since Q1 could just go to Q4.
Yeah, this is kind of a duplication of that logic.
So, another one.
What would the final DFA look like? Actually take a stab at drawing that fully reduced DFA. And the question, in fact, take note of this. And if you'd like to do something fun, fun puzzle for you between today and tomorrow. Actually draw out the best DFA that you can between today and tomorrow, and I will start tomorrow's class with how many nodes was the best DFA that you could find. And we'll see if you can find the one with the minimum number of nodes, minimum number of vertices. That's all the time we have. So I will leave you to do that. We will gather tomorrow for an answer to this as to what is the smallest possible DFA that is equivalent to this one. And we'll go into a technical algorithm for reducing a DFA into a minimum DFA, because that is something useful that we should know how to do. Questions about anything that we've covered today? Anything about this? Kind of giving you a teaser?
On the homework, we expect all of our DFAs and NFAs to be in reduced form?
No.
Okay.
If it asks you to just find one, any of them is fine. Only if the question says, find a minimum DFA, will I expect it to, you have gone through this process. All right, we'll see you all tomorrow.